So today we'll be talking about chromatography. I apologize if I'm a little out of it today. I'm still recovering from a cold. I currently have a fever, but science waits for no one. So let's dive straight into it. So chromatography. Let's start with our motivation. Imagine, let's just say we had a cell, right? A very nice cell, and we lysed it. All right, we lysed it. Boom, he blows up, and he's filled with proteins, right? Let's say the nucleus is still there somehow, right? And then we put him into a little vial. All right. And now this vial has a bunch of nice proteins in it, right? And now, well, it's not very useful. The proteins are too small for us to manually pick out, right? But let's say we want to separate these proteins somehow. That's where chromatography comes in. And basically, chromatography gives us a way to basically separate these proteins based on something. All right, it can be, let's say, it can be size. It can be like polarity, hydrophobicity, right? A lot of different types of interactions, we can now filter out these proteins. And that's basically what chromatography will let us to do. It'll basically let us take this vial, which is a bunch of proteins, and sort them based on some sort of property that we want them sorted by. And you can imagine how important this is, because we can't really just go in there and pick up proteins ourselves, right? We got to do it through their properties. So let's just go over what chromatography exactly is. So obviously I just said it's a technique to separate components of a mixture. And usually it's proteins in this case, right? Especially as a molecular biologist, you're probably going to be dealing with proteins most of the time. But you can also separate different components, right? You can separate just like organic compounds in general, right? Hydrocarbons in general. You can even do non-hydrocarbon, like non-organic molecules as well. But usually it's done within the context of either like organic chemistry or biological compounds. And today we'll mostly be focusing on proteins because that's usually where most of the interesting stuff happens. And what we want to see is how long this protein, right, will stay in some matrix. So imagine we have a matrix here, right? And let's say we throw a bunch of proteins there, and then some protein leaves. And I'll give you an analogy. Imagine we have a little tube here, right? And imagine in this tube, we want to measure well, let's say people are going through this tube, right? People are going through this tube. And let's say we want to filter out these people somehow. Well, we just have to make this tube have some sort of property. Okay, maybe this analogy is a little loose, but we want this tube to have some sort of property such that, let's say we want to filter out this tube from weakest to strongest. Let's say we want to be able to separate the strongest people from the weakest people that leave this tube. Right, there's just a tube they can just walk through, right? So it's like, this is not going to help. If we just let them through, they'll all go through at the same time, right? Doesn't really help us. And so we need a way to basically change the retention time of each person. Imagine this guy's really strong, this guy's really weak, but they're going to leave at the same time, right? So we need to do something. That's where we use our stationary and mobile phase. So what exactly are these things? The stationary phase, think of it as like a ladder in this tube. Let's say the ladder goes this way. All right, just bear with me. I never heard this analogy before. I came up with it. Hopefully it makes sense. Boom, ladder. That's our stationary phase. It's basically something for these guys, right? The proteins we're going to analyze to hold on to. All right. In practice, this is probably going to be some sort of ligand, right, or some sort of something, right? In this case, it's ladders. But again, same idea, right? I mean, if these people just walk, they're going to leave at the same time. Maybe some idiot will, start playing with the ladder and then they leave later, but it doesn't really help us, right? But now we add a mobile phase. What the mobile phase basically does is it basically pushes the people through, and whoever dissolves the fastest in that medium will exit fastest. So in this case, imagine we have a bunch of water, right, rushing through. Let's say this is water, H2O right there. Water is rushing through. And obviously these guys are going to get pushed through, right? And these people are called analytes, right? These are things we want to analyze. That's why they're called analytes, all right? Usually they're proteins, could be organic molecules, who knows? But either way, these people are analytes. And once this water rushes through and they go through the tube, obviously what are people instinctively going to do? Well, they're going to go grab the ladder, right? So who's going to leave first? Well, it's going to be the weakest people, right? The weakest people can't hold on strong enough, and they'll end up getting cast out. And so whoever leaves first, right, this guy's weak. This guy's a weakling. And then whoever leaves last, or doesn't leave at all, right? Those are the strongest. And now we've found a very good way to now separate these things. This analogy might be a little loose, but all you should take away: stationary phase, something for the analytes to grab onto; mobile phase, something for the analytes to dissolve into to potentially get carried out of the system. That's basically where chromatography is based in. So now I want to go over a bunch of... Oh, actually, no, before I go over the chromatography techniques, I want to review some prerequisite. This might take a little bit. If you're already familiar with everything on here, skip ahead. I just want to, really nail down a lot of this prerequisite that you need to know to understand chromatography. So first, we want to talk about polarity. And what exactly is polarity? Well, polarity is basically the net charge on some sort of bond or molecule or whatever. More so the fact of, let's say you have an identical, or not even identicals, any compound, is one side gonna have different properties than the other. That's basically what polarity means. In our case, is this side positive and is this side negative? You might have seen this delta sign before, right? And so obviously what you can imagine as the most polar is a salt, right? Let's say we have a salt and you have a positive cation and a negative anion, right? This is very polar. This guy's extremely positive. This guy's extremely negative. With something a bit less polar, water molecules. Let's say this is oxygen. These are hydrogens, right? Oxygen is a lot more electronegative, so more electrons get pulled inwards. So we have a positive charge on the outside and a negative charge near the oxygen, right? This is a polar molecule. This is one of the most polar molecules that don't edge into ionic stuff, right? And so they actually form H bonds. But we'll get over that a bit later. But I want to go over the fact of like dissolves like. Imagine we have something that's nonpolar. Let's say we have some benzene thing, right? And then we have another benzene thing. All right. Why is it? Or if you imagine oil, right? You've probably put oil in water before. Why does the oil always mesh together and stay together and not just dissolve in the water? Well, there's a very simple explanation of that based in entropy. I'm assuming you know what entropy is, but if you don't, you can probably still understand this. When these two are dissolved in water, right, we know that they're going to go together, right? Basically, they won't dissolve in the water, they'll group together. Why? Let's see. I'm going to note water in blue. When we have a bunch of water molecules around these guys, right? Since these guys are non-polar, these water molecules aren't going to be able to really bind very well with them, right? For example, let's say this is just it's an aromatic ring, right? So it's just a hydrogen and a carbon, nothing really special, not particularly polar, right? It'll still dissolve a little bit, but it won't dissolve nearly as much. And so the water, they want to form H bonds with each other, right? That's their most energetically favorable conformation, is when they're all H bond together and they're kind of just chilling out, right? And so let's imagine the same thing over here, right? But okay, so now we have two, hydrophobic or two aromatic rings that each have a bunch of water around them. But this has a lot of this is a very ordered position, right? There's not a lot of microstates that this guy can exist in, right? There's kind of just this. But imagine the contrary. Imagine if these two rings are on top of each other, all right? Okay, imagine that's a ring down there, all right? Now what? When these rings are overlapped on each other, right? Obviously, we still have our water, right? These guys are very, very ordered. But look at all the other water that we got rid of in between, right? Those guys are just floating around. And these guys can do whatever they want. These guys can arrange themselves in however many ways they want. And this is very disordered, right? High entropy. And so we see that, I don't know if you can see that, hold on. High entropy. So we see that this is more entropically favored, right? This has higher disorder, meaning, and we know that the universe tends towards higher disorder, right? And so that's sort of the reason why like dissolves like, is because non-favorable interactions, right, mean that when the solvent wants to dissolve this thing, it will form more microstates if this thing were closer together and the surface area was minimized, right? That's sort of the idea of what like dissolves like. And now, now I want to talk about molecular interactions. Right, probably should talk about this first, to be fair. Either way, or whatever. We have 4 types that we really want to talk about. Obviously, there's more. There's like metallic, right? And then there's like covalent and whatever. I just want to talk about 4. One is dipole-dipole, right? You should know how this usually works. We have some sort of atom and another atom that are covalently bonded, right? One has a higher, let's say this guy has a higher electronegativity. This guy has a lower electronegativity. The one with the higher electronegativity, let's say, has more protons, right? And and the electrons aren't proportionally as much, is going to attract more of the electrons. Imagine we have the bond as electrons, right? It's going to attract the electrons closer to it. And the more electropositive atom, right, therefore has less electrons. So this guy's a more net positive charge, this guy's a net negative charge. That's a dipole, right? And imagine we have another equal, right? Same molecule, right? Oops, this is negative. These guys are going to form bonds. Not bonds, but they're going to interact, and that's they're going to attract each other, right? Common, like magnets, right? And when this is part of H, and H is bonding with N, O, or F, right? These are very electronegative atoms, right? When H is bonded with these, they will form something so polar that when they interact with each other, they form something called an H bond. Another one is a carbonyl, COO and this H. This is also just as polar as well. So this also counts as one of like the H bond group members. And this is just like a dipole-dipole interaction on steroids. Like they're like super strong. That's why water is extremely good at dissolving anything that's remotely polar, because they're strong, right? And also why water is bad at dissolving things that are non-polar, because they're super strong. These water want to bind to each other and not so much the thing inside. Another thing we want to talk about are London dispersion forces. And this is basically when if we have 2 atoms, right, and we have some electrons, right, over time, these electrons, right, let's say we have a bunch of electrons, just by random chance, they're going to interact with each other to repel each other, right? And if by just chance, some of them get repelled to one side, right? Then this forms a pseudo dipole on the atom itself, right? Where there's more electrons on one side, less electrons on the other side. And what does this positive side do? Well, it's going to attract electrons. Electrons are going to go towards that side too. And what we see is we have like a very unstable but still meaningful interaction between 2 molecules based on where one has electrons, where it doesn't. And this just spontaneously forms with any molecule that has electrons, right? And so we have like a pseudo dipole within the same atom. And this is very strong. These interactions are very strong in very large molecules. So imagine you got a huge molecule and what is something that has like a million benzene rings, right? Like a bunch of benzene rings, right? Like this is gonna have very strong LDFs, whereas it doesn't have a lot of H bonds, right? But these interactions are a lot weaker than H bonds or dipole-dipole forces, and that's the difference of they're not going to dissolve each other, is what I'm saying. Or at least they'll dissolve each other very poorly. The next other one is obviously Coulombic or ionic forces. This is just like if you have literally like a positive ion, like a straight up like Na plus, right? And like a Cl minus. Okay, they're gonna love each other, right? But interestingly enough, these guys do dissolve in water still, which is pretty interesting. And then we want to talk about hydrophobic and hydrophilic compounds. Hydrophobic just means it doesn't dissolve in water, whereas hydrophilic means it does. You also think of it as like going towards water, going away from water. It just means they don't dissolve. So something that's hydrophobic, imagine oil, right? Or you ever see those leaves, wax, right? If you see the leaves that you drop like a piece of water and it looks like very, very, like it doesn't like dissolve at all. It's like very, round and smooth. That's a hydrophobic surface. Hydrophilic, think of like our skin, for example. If you put water on it, and you try to shake it off, some of it still stays on because your skin is still a little hydrophilic. Something else is hydrophilic. Salt, right? Salt is very hydrophilic. Just think of any polar compound, right? And then talking about water, we also want to talk about aqueous and immiscible. So aqueous just means it's going to dissolve, right? An aqueous solution, right, is if you, let's say we have solution A, right, and we add a bunch of solution B. Imagine this is liquid. Well, we're going to get just like a homogeneous solution of A and B, all dispersed in there, right? That's aqueous. Immiscible is when they don't dissolve in each other. So imagine we have A and B. Well, let's say we have A, and then B is just chilling on top, right? They're immiscible because they're not dissolving each other. So for example, this can be water, and the other thing could be oil. Common example. That's about all the prerequisites we want to talk about, and this should give you a nice foundation of how these techniques work in concept. All right. First, affinity chromatography. We want to start out with our matrix. All right, this is going to be our stationary phase. If you remember what we talked about, stationary phase is like the ladder of like the sewer pipe. I really hope that analogy works. Right? Something we can use for this one, it has to be inert, right? So we can use like polyacrylamide, just like an electrophoresis, right? Agarose is also a good one. Just something where, I'll draw it here, something where we can put in these things called spacers. And what spacers will do, right, is they'll bind to the, let's say polyacrylamide, right? Let's say we have 100 polyacrylamide. These spacers will bind onto it. And also these spacers will bind onto some ligand, all right? This ligand can be anything we really want, so long as it's pretty small. And then our mobile phase, remember, like the water that we're pushing the little guys through, is any mixture with analytes, which are just like, you know, any proteins, right? And basically what this will filter out is any analyte that binds to the ligand will pass through the matrix slower, right? If you imagine you had protein A and protein B, let's say protein A had interactions with the ligand. Well, it might just like chill out here for a little bit, right? And then okay, it's gone. Oh, I might chill out a little bit more with all the ligands down here. Okay, it's gone, right? Whereas this guy, let's say this guy doesn't really care about this ligand at all. He's just gonna go straight through, right? And so we see the retention time on analytes that don't bind with the ligand is lower than the retention time of the proteins that do bind with the ligand. All right, I'll say that again. Analytes that don't bind with the ligand have lower retention time, meaning they will be the first ones to leave. Analytes that do bind to the ligand will have a higher retention time, meaning they're the last to leave. So you can imagine how we can separate these proteins, right? And this is very common for substrates and enzymes. Imagine the ligand is a substrate, right? Let's say the ligand's like phosphate, and then we put a phosphatase as one of the enzymes. The phosphatase is going to bind with, like, the binding site of the phosphatase is going to bind with the phosphate. That's an interaction, right? And they're just going to be chilling there, right? Whereas, let's say you have something that doesn't bind with phosphate, like, I don't know, like lipids, right? They're just going to go straight through because they don't really care about the phosphate, right? And that's sort of how affinity chromatography works. I don't want to go through the procedure since I'm myself not too familiar with that, but this is the concept of affinity chromatography. Next up is normal phase chromatography. This is sort of like usually never discussed, but it's to lead into the next one, so you get like some sort of like, you know, whatever. The stationary phase is we have these solid beads, all right? Usually they're like silica or something. And these beads are coated with a liquid that is polar. So what's going to dissolve in here? Think about it. Sugar can dissolve in here, or ions can dissolve in here, right? It's polar. And the mobile phase, okay, so we have a bunch of these beads, right? In like a big column, right? Okay, let's imagine there's more, right? And the mobile phase will be something that's non-polar. So let's imagine like hexane or chloroform, right? And in this mobile phase, there's also the analytes that we want to analyze, right? And what's going to happen is that the polar analytes will interact more with the polar stationary phase, right? Whereas the non-polar ones, they're just going to pass straight through. So the polar analytes, this should be slower. This should be faster. The polar analytes should be slower, and the non-polar analytes should be faster, right? Because the non-polar analytes, they're not going to really care about these beads. They're gone, right? Whereas the non-polar, or there's the polar ones, they're kind of chilling in here, right? They might dissolve in here a little bit, be like, okay, I see what's up, and then they go to the next one, right? And so they have a big difference in retention time. So whatever leaves first is going to be non-polar, right? And whatever leaves last is probably going to be polar. And this is used very commonly for very polar compounds, such as, let's say, amino acids or sugar, right? That's normal phase chromatography. On the contrary, we have reverse phase chromatography. And this is the exact same thing, except these beads now have aromatic side chains, right? And aromatic is just a fancy word for non-polar, basically. No, it's not, but like, okay, it's non-polar. Imagine this is non-polar, okay? And then this non-polar ligands, right, these aromatic side chains, will have a non-polar solvent that can now, chill there, right? Because now it can bind to the, it can interact with the ligand and it'll chill there. That's a solvent. And imagine we have the same thing, this continues, right, in the column. So this is pretty messy. And then the mobile phase will be a polar solvent like water or methanol, right? And now imagine what's going to happen. The non-polar analytes are going to chill in more. I made the same mistake here. Slower. Faster. They're going to chill and interact more with this non-polar solvent. And they're going to chill in more, and they're going to have a higher retention time. Likewise, conversely, the polar analytes will just pass through because they don't really care about the non-polar solvents. They're just gone, right? They're not going to dissolve and interact with it. So what leaves first? Well, what leaves first is the polar analytes, and what leaves last the non-polar analytes. And this is very commonly used for non-polar to moderately polar compounds. Proteins are a big one, for example. That's why we usually hear reverse phase chromatography more often than normal phase chromatography. Because if we're analyzing proteins, which we usually are, this method can distinguish them better, right? Whereas the other one, if you have something that's like non-polar, right, they're gone. We can't really distinguish non-polar from non-polar. Whereas this one, we can actually see like what's more non-polar versus something else. Because whatever leaves first, they're all pretty polar, right? That's sort of the idea. Okay, hydrophobic interaction chromatography. This one is very similar to reverse phase chromatography, but is different in how it works, and I'll go over it now. Again, stationary phase, same thing. We've got beads, right, with non-polar ligands. Now that they don't have a non-polar solvent on them right now, okay. And the mobile phase is aqueous solution, right, so full of water with a very high salt concentration. Okay, so imagine, and our analytes, they're typically proteins. Imagine we have a protein, and this protein is going to have hydrophobic and hydrophilic sections, right? Some more than others, some less than others, right? Let's imagine the black is hydrophilic, and the yellow is hydrophobic, yeah? I don't know if you see that, but yeah. So these hydrophobic regions are going to interact with this ligand, right? Imagine we have our protein, and we have a bunch of hydrophobic stuff on there, and the hydrophilic stuff. There's me chilling there, right? Now, and what else do we have in here? We have free-floating water, right? But the water is like all surrounding these salt molecules, or the salt ions, right? Imagine we have our Na plus here, right? This water is all huddling around, right, with the oxygen, looking at the Na plus. Likewise, if we have Cl minus as well, right? We have Cl minus. We have all the hydrogens facing the Cl minus, right? Because the hydrogens have a net positive dipole. And so we have a lot of these ions to basically keep the water busy, right? The water doesn't really care about the proteins right now. That's why, okay, so right now, let's say we have let's say 100% salt concentration. We're going to now add in a buffer, or obviously water's leaving here, right? Well, we connect this water to we're basically titrating this, right? And we're getting a bunch of stuff leaving. We're going to start adding a buffer with 0% salt concentration, or something very low. And what's going to happen is that these ions slowly, disappear, right? Not disappear, but like, okay, now there's not as much Cl. What's this water going to do? Well, this water is going to interact with the proteins now, right? There's nothing to keep the water distracted. And so this will destabilize the hydrophobic interactions between the ligand and the proteins, because water is now fighting for this protein, right? And so this increases analyte solubility if we decrease salt concentration, right? Now, what's retained the longest? What's going to leave these ligands the fastest, right? Well, the compounds that aren't that hydrophobic are going to get carried away right away, right? Think about it. If you're mostly hydrophilic, and now the water is now like, looking at you and wants to bring you down, you're going to go with it, right? The ligand isn't that strong. Whereas let's say you're a very hydrophobic protein, you don't care about this water, bro, just leave, right? So if you're hydrophobic, you're going to stay more on the ligand. If you're more hydrophilic, you're going to leave. And so whatever requires the most free water molecules, right? Just water molecules that aren't, in an interaction with an ion. Whatever requires the most is going to be retained the longest, right? Meaning they're the most hydrophobic. And that's sort of the idea behind hydrophobic interaction chromatography. Likewise, hydrophilic interaction chromatography is a very similar concept. It's just basically reversed. So now, instead, we'll draw it down here, we have beads with polar ligands. All right, we got polar ligands on here now. And now, for our stationary phase, for our mobile phase, we have water. All right, a little bit of water. But we have a very high concentration of an organic solvent. What we usually use is acetone nitrile, all right? And we have a very high concentration, up to like 95%, okay? And so what happens originally, or normally, is that we have our analytes bound to the ligands. Now this time is reversed, right? Now it's the hydrophilic sides bound to the ligands, and the hydrophobic sides are just chilling, right? And this organic solvent, right, obviously does interact with the hydrophobic section, but it's not going to really dissolve these proteins as much because, like we said, polar interactions, like dipole-dipole interactions, are stronger. H bonds are stronger. So these guys will kind of just be chilling there. Maybe the very hydrophobic proteins will get dissolved, right? But let's just assume they're all kind of just like chilling on the ligands. Now what we're going to do is decrease the concentration of acetonitrile over time. And what is this going to do? Well, this is basically the equivalent of increasing water concentration, right? Because we have such a high concentration of this solvent that decreasing this concentration is basically just adding in more water, right? And so when we have more water molecules, now these water molecules are going to compete, right? Water molecules, they're going to compete for the hydrophilic proteins, right? The polar ligand might not be enough anymore. And so as you get more and more water, right? As water comes in more, it's gonna try to snag away the hydrophobic regions of these proteins, and sometimes they'll win, and they'll be flushed down. So what are retained the longest then? Well, what's retained the longest are the molecules that require the most water to pull them out, and that's the most hydrophilic proteins. The most hydrophilic proteins will stay connected to this polar ligand as long as it can, and usually this is a very polar ligand, right? Very, very polar. But eventually, there's too much water. Water is very, very good, and it's very small, and it'll wiggle its way down there, right, and destabilize it and pull it away, right? Basically dissolve this protein, right? And so it takes, whatever takes the longest to dissolve is going to be the most hydrophilic. So what leaves first? Hydrophilic. What leaves last? Hydrophilic. That should make sense. Usually we see hydrophobic interaction chromatography used a bit more, but we still see uses for hydrophilic interaction chromatography as well. So they're basically mirror images of each other. In my opinion, hydrophobic interaction chromatography makes a bit more sense, but this one also makes sense as well. Next up, we have size-exclusion chromatography. This, like in its name, will distinguish proteins based on size. So what we have see our stationary phase, right? We have these porous beads, and these porous beads, let's imagine like a sphere, right? Have little holes in them, and these holes have different have one set size, and we call this the size exclusion limit. And basically, what happens is, let's say we have a bunch of analytes, right? All the analytes that are small enough, which are under, the size exclusion limit, is going to get stuck in these little beads, and they'll make their way out eventually, right? But think about it, they gotta bump into a bunch of like walls and everything before they find their way out. That's gonna slow them down. Whereas the big stuff, they're just gonna like zoom around, right? And so what leaves first, right? What's retained shorter are the large particles, the particles that are larger than the size exclusion limit. Whereas the particles that are smaller than the size exclusion limit will be retained longer because they'll be stuck in the little beads for longer, right? Imagine like we have like hundreds, thousands, millions of these beads, right? And so on the right, you can see a little graph of so down here is the fractions, and the smaller the fraction number is, the shorter it was retained. So imagine it's like time, right? Imagine like 1 is like after 5 seconds, 2 is after 10 seconds, 3, etc., right? What leaves first are particles that are bigger than the cutoff, right? That should make sense. And then what's smaller than the cutoff are retained longer. And that's what we see here. But we have some overlap, right? Because by random chance, right, some of these large proteins, they might be a little unlucky and hit a bunch of pores on the way down. And some small proteins will get real lucky and zoom right through the pores somehow, right? But to minimize that chance, what we can do is actually increase the column length, right? Or decrease the pore size. And what this will do is basically minimize probability from having this, cross contamination. In other words, it just makes the fractions longer, right? It'll take longer for these small proteins to leave. The only caveat to that, especially decreasing pore size, is that obviously if you decrease pore size, you're not really, filtering your protein nearly as well, right? A big use of size-exclusion chromatography is when we have a bunch of extracellular vesicles and a bunch of free protein, and we just want the extracellular vesicles. Because extracellular vesicles are huge, whereas free protein is pretty small. And so we want to just purify it, basically. That's usually the biggest use of size-exclusion chromatography. And people usually run this like a bunch of times until they get it fully purified. But yeah, that's basically how size-exclusion chromatography works. Pretty straightforward. Now I want to talk about ion exchange chromatography. And this one's a bit more complicated. And I'll split it up into two parts. First one is cation exchanger, right? Chromatography. And cations, remember, they're positive ions, right? Cats are positive, right? You love cats. And then anions, not a cat, it's negative. No cats, bad, right? And so they're negative. And so cation exchangers, remember, they're exchanging positive stuff. What does that mean? Well, we're going to figure out. Anions, negative stuff. Okay, let's first start with cation exchanger chromatography. Our stationary phase are beads again, rubber beads, that have a net negative charge. Maybe on the outside or they themselves are made of something that has a net negative charge, right? And so we have negative charges on them. That's our stationary phase. Imagine we have a bunch of beads with a bunch of these. For our sake, I'll draw them like this because I think it'll be a bit easier to show what happens. And I'll just write a big negative sign on here. And our mobile phase is a buffer with a bunch of positive ions and a set pH. Now this should sound familiar. It should ring a bell for isoelectric point, right? Remember, if we have any generic protein, right, we have our anomeric carbon with our carboxylic acid, right, and our amide. At a low pH, right, this guy is protonated, and this guy remains there. He's positive, right? Let me move him. At our intermediate pH, this is our carboxylic acid will deprotonate, right? And what we're left with is a net neutral charge, NH3 plus. And then at a high pH, our amide, right, will deprotonate and give up its proton, and we'll have a net negative charge. Oops, this should be negative. Right? Positive, neutral, negative. So we set our buffer pH to a certain pH where we know how the proteins are going to react, right? Proteins have different isoelectric points. Some might be neutral, some might be positive, some might be negative, okay? And there's positive buffer. So first we add in our positive buffer with no proteins. So what happens? Let's say we have like sodium, right? Sodium chills there, right? Or we have, let's say, or usually it's bigger positive ions, right? So imagine we have a bunch of positive ions, and now basically this is what we call conditioning, right? We basically conditioned now this stationary phase to have a bunch of positive ions just chilling, right? Now what do? We add the same buffer, but with our protein now. And imagine we have a bunch of different proteins. Some of them are going to be negative, right? If the pH is higher than its isoelectric point, right, they're going to become negative. And what are those negative proteins going to do? Well, imagine we have a negative protein. They're repelled by these beads, right? So they're just going to go straight through. What about neutral ones? Well, neutral ones, they might just chill and they're just going to fall, but they might chill out a little bit more than the negatives at least. And what about the positive proteins? They're going to actually displace, exchange themselves with these positive ions, and they're going to interact with these negative beads. All right, so they're going to be retained longer. I think on the next slide, yeah. So the negative proteins, right? If we imagine here, negative proteins are going to leave first. Positive proteins are going to leave last. Right. And so first, what do we have after we put in the buffer? Right, we have a bunch of these negative charges, and all that's left in here are positive proteins. Proteins whose isoelectric points are lower than the protein than the pH we set the buffer to. Okay, so all that's left are positive proteins. Amazing. All the negative proteins are gone. We can collect them in a little whatever. Right. Now what we do? Obviously, in this solution we have a bunch of salts, right? And we also have protons. We can increase either the salt concentration or the proton concentration, which would either increase the pH or increase salt concentration, depending on what we do, right? Let's first look at salt concentration, increase in salt concentration. What's going to happen when we increase salt concentration? Well, if we increase more positive charges, right, a lot more positive charges, okay, let's assume positive charges, ions, are red. They're gonna fight for this negative bead, right? If there's enough of them, they're gonna fight for this negative bead. And how long this protein stays on depends on how positive it is. So if this protein is very positive, right, then it's going to stay on, and we're gonna have to have a much higher salt concentration. Now, if the beads aren't as positive, they're gonna dilute. They're gonna elute. Sorry, they're gonna leave because they'll get outcompeted by these positive ions. And so what leaves first? Okay, so for what leaves first? First, we have our negative proteins. Makes sense, right? That is the no chance. Second one are positive proteins that are kind of positive. And third, lastly, we have our mega positive proteins that could really stay onto the bead. And so that's how we've separated these different fractions, and these proteins have different retention times. Likewise, if we increase pH, what's going to happen? The proteins whose isoelectric points are those proteins whose isoelectric points are much lower are going to get eluted lastly, right? Imagine you're increasing the pH slowly, right? What's going to happen? Well, we might have, imagine this is our pH scale, right? Let's say we have protein A. Protein A has a isoelectric point here, right? And then protein B has an isoelectric point here, right? If we're increasing pH slowly, right? These guys, let's say the pH starts here. Sorry, let's say pH starts there. Obviously, these guys are both positive, right? If we look back here, we have a low pH, so they're both positive. But they're going to become negative soon, right? If we're increasing pH, they're going to become negative soon. So what's going to happen when the pH gets above this one? B is going to turn negative, right? He's going to get repelled by these beads and leave. And so basically what we've done is basically turn a B into a negative protein by increasing our pH to where it's going to leave now, right? And so now we've sorted the proteins based on isoelectric points. That's the beauty of cation exchanger chromatography. I hope that made sense. I'm going to go over again with anion exchanger chromatography. And this is the exact same, literally the exact same, except flipped. Right? Now our stationary phase, right, instead of being beads that are negative, they're not positive. Who would have thought? Right? In our buffer, instead of negative anions, we have positive cations. Or sorry, instead of positive cations, we have negative anions as our buffer ions. And obviously we also have to set pH. Same thing before, proteins will have different isoelectric points. Now we first add our initial buffer, right, without the protein, and okay, now we condition this guy, right, and we've coated all of them with these ions. And then we add with the protein, and these proteins, some might be negative, some might be positive, right? What are the positive proteins going to do? They're gone. They're zooming through, right? They're not going to interact with this bead. They're going to be repelled by the bead and just move straight through. The negative proteins, on the other hand, will displace some of these ions, right? There's not that many of the ions. They're going to displace them. And so now, obviously the positive proteins, they're all gone. They've all eluted, right? Negative proteins, they're just chilling in there. And now, exact same thing. Increasing salt concentration, remember, it will compete more salt here, right? More negative anions here. It will compete more with the negative charge, and the negative charges that aren't net negative are going to get, evicted, right? Whereas the very, very negative proteins will stay on for a bit longer. And so that's one way of keeping of differentiated retention time. Other one is decreasing pH. Last time we increased pH to get it above the isoelectric point to turn the proteins negative so that they would leave. But now negative is good, right? So now we want to do the opposite thing. We want to turn these proteins positive. And how we do that? Well, we decrease the pH. We get the pH under its isoelectric point, and that will turn them positive. Remember, that means more of the carboxylic acids will take up more hydrogens, right? And the amide would still have its little what's it called? Still have its hydrogen, and it makes it net positive. So we can decrease pH, and whatever leaves first will have the higher isoelectric point. Whatever leaves last will have the lowest isoelectric point, right? That should make sense. Hopefully that makes sense. Basically, it just sorts proteins based on isoelectric points, and it's a very neat way of doing it. Okay, lastly, we have thin layer chromatography. And this one's the most common one you would use. Some people do this in high school, university. It's a very easy way because it's just like a little slip of paper, and you can just do it. It's not paper, but it looks like paper. And basically, what this is, and basically we start with an inert slide. All right, this can be silica or alumina, right? Just inert. He doesn't do anything. And we coat him with some absorbent. I think this should be A. I can't spell A. Oops. Yeah, A. And We coat them with a bunch of absorbent, right? Put them in the oven, bake them, so all the moisture leaves. And now what we have, just imagine him as like a piece of paper, right? What do you do what happens to paper when you put it in water? Right, it gets wet. That's basically what this guy is meant to do. Right, he's a piece of paper, right? And now what we do, we have something called a start line, right? Start line. And we basically drop our analytes on here, right? Let's say we have analyte A, we drop it here, analyte B, analyte C. A, B, and C. We just drop them, like maybe it's like pipette or whatever, right? And then now what do? We now have, let's say we have a big beaker, right? And we now submerge the bottom part of this sheet with the mobile phase. And what's going to happen? All right, let's say we have our mobile phase. What's going to happen is the mobile phase is gonna go up on the sheet from papillary action, right? Imagine you put like a piece of towel in water, water will rise in there, right? Same idea, capillary action. And analytes that can dissolve in the mobile phase will get carried higher, right? Something that's very commonly used is you'll have a very soluble mobile phase, can even be water, and then you have these analytes that have different properties of polarity. And the analytes that are more polar will get dissolved in the water and be brought up with the water as it goes up. And we basically stop this. We take out the slide. Once the capillary action has reached us end line, right? Or we call this the solvent front. Solvent front. And this something can also be nonpolar, right? You can do that either way. Like you can use hexane, you can use water, whatever. And now on the right, we can see some of these results, right? We saw this protein, right, that was dyed, rose higher than this protein. And by the way, we can either dye this at the beginning, or we can, view them under UV light if they're like UV. If they're fluorescent, right, we can see them under UV light. Or if they're absorbent, right, we can see dark spots if we shine light on them, right? If we shine light and some of them are dark, then it's probably, that's where the protein is, right? Different ways of dyeing it, usually you just use a dye. But we see that this protein rose higher than the other protein. That means it was more dissolvable, more similar in property to the solvent, whereas the other one is more similar to the stationary phase, right? That's basically TLC. And I also want to talk about calculating what we call RF values for TLC. Imagine we have this little thing, right? This is our sheet. Start line, solvent front, and we have protein A, B, and C. How do we know what these proteins are? And obviously they're quite hard, but let's say you know this mixture has, let's say you know what protein, what 3 proteins are in this mixture, right? And then now you need to assign them. What we have come up with is something that's very, very genius. We have come up with something called RF values. And basically what this is, right? RF is a unique number attributed to each protein and is calculated by this. It's equal to the distance, right? Let's say distance is between the start line and the solvent front. Distance goes to the bottom of this fraction. And what goes to the top is how far this protein moved from the start line. Let's call this S. S over D. Basically, the fraction of the distance that the protein moved. And this RF value, we have known RF values for a myriad of proteins in a myriad number of solvents. Remember, different solvents, you'll get different RF values. Different proteins, you'll get different RF values. But if you have the same solvent and the same protein, they're going to have the same RF value. Should make sense. Because, science works, right? And so if we know this RF value, right, is like 0.5, this one's 0.7, this one's 0.3. We can match those values to the proteins that we know are in this mixture. And if we know, let's say the protein in this mixture that has R value of 0.7 is, I don't know, like insulin, then we know protein B is going to be insulin, right? And this is basically how we can determine which proteins are which in a mixture. The tough part is when there's a bunch of proteins that are very similar in height, and so it's much harder to figure out the R value to a very very pristine, very precise extent. But it works with R values that differ quite a bit. Okay, we covered a lot today. We covered a bunch of different techniques. Let's do a quick recap. First, we talked about affinity chromatography, right? Remember this one, we had like a polyacrylamide gel, right? With a bunch of spacers, with a ligand bound on, and we put our analytes through, and whatever analytes had binding with this ligand will be retained longer, and everything else will be gone. This is very useful for enzyme, substrate, analytes. Okay, next one, we had normal phase chromatography. Remember, we had our beads with our polar with our polar solvents around them, right? In our little column. And then we put our analyte through in a non-polar mobile phase. And whatever was retained longer was more polar because it interacted more with the polar beads, the polar solvent on the beads. Whereas what was non-polar just kind of skimmered through. So non-polar, then polar, right? Conversely, reverse phase chromatography is the complete opposite. We had our beads with our aromatic rings, aromatic side chains, right? And these guys had a non-polar solvent around them, right? And then we put a polar mobile phase in them. We'll use first polar, then non-polar, right? Now we go into the more advanced versions of these respective, chromatography methods. We have hydrophobic interaction chromatography. Remember, we had our little column, right, with our beads. And on these beads, we had hydrophobic side chains for them to bind to, right? Hydrophobic ligands. And we had proteins. We add our protein in, and our proteins will bind to these ligands, right? And we have a very, very high salt concentration in our mobile phase. Very high salt concentration. What we do is we lower our salt concentration such that eventually the water will overpower these interactions. And so what we see leaves first is the most hydrophilic, then the most hydrophobic. Right, because the most hydrophobic remained on these beads longest. Conversely, hydrophilic interaction chromatography is the opposite, right? We had these beads with polar side chains or ligands, and we had also an aqueous mobile phase with a very high concentration of these organic solvents that we used. That's usually acetonitrile, right? And what we do, obviously these proteins are bound to these hydrophilic ligands. I don't know if you see this actually. And as we decrease the concentration of acetonitrile, right, what's going to lead first? Well, the most hydrophobic is going to lead first. Because what we're basically doing is adding in more water into the system, and that's going to compete with the polar ligands for these molecules. Then, what leads is the most hydrophobic. Then we looked at size-exclusion chromatography, where we had a bunch of porous beads, right? with a certain size exclusion limit. And all the proteins that were under that size exclusion limit got stuck in those pores and subsequently left the pores later, right? So what leaves first? Large, then small. All right. Then we looked at ion exchange chromatography, and we have two types, right? We have two types. We have our cation exchange chromatography and our anion exchange chromatography. Remember, our cation, right? We had negative charges with positive ions, and what left first were negative proteins, then somewhat positive proteins, and then very positive proteins. That was the order that our proteins eluted, right? And this was based on their isoelectric point. Our anion exchanger chromatography had positive beads with anions on these beads, right? And what left first? Let me just move this over here. What left first are positive proteins, right? Positive proteins didn't want to mingle in there. They left first, and then our negative proteins, and then our very negative proteins, right? Increasing negative, increasing positive over here, right? Should make sense? This is also based on their isoelectric point, in which we increase salt concentration for either, right? We can either increase salt concentration, right? Increasing positive charges. Here we'd be increasing negative charges. Or we can increase pH on this side to shift the isoelectric points off to where the proteins become negative and thus leave, right? And we're also sorting them based on how positive they are, or sorting them on their isoelectric point rather. And in this case, so increase pH. And in this case, we decrease pH, right? Shifting them the other way to become positive. And once they become positive, they will elute. And so this way was sorting based on isoelectric point at the end of the day. And lastly, we looked at TLC, right? Where we just had a sheet of an absorbent. We had our start line, finish line, right? We put our analytes on separate little parts. This is our stationary phase. We put them in some mobile phase. Mobile phase can be polar or non-polar. And through capillary action, it will bring the analytes up. And based on how soluble the analytes are in that mobile phase, it will go up higher or lower. Right? What goes higher? Things that interact more with the mobile phase. What it doesn't go as high? Things that don't dissolve so well in the mobile phase. And we talked about how RF values can help us determine what these proteins are. That was basic chromatography. This was not meant to give procedural tips or anything. This is purely conceptual. I haven't done many of these techniques myself, but I know of them and I have studied them. And hopefully the concepts make sense. Running them themselves is a whole different story because there's a bunch of different ways. Like hydrophobic interaction chromatography is like a high pressure liquid chromatography method, or high whatever. I don't even know to be frank. But this is sort of the conceptual idea behind all of these techniques. Hopefully it helped. Hopefully you learned something. And yeah.